Yes, welcome. My name is Osekunweno Martin, and this is our week 6 assignment. We are given to review a paper, and the title of my paper, which I was given to review, it's called Deep Breath Automated Detection of Respiratory Pathology from Lung Auscultations in 572 pediatric outpatients across 5 countries. So the keywords in this paper, there are respiratory pathology, lung auscultations, deep learning, and classification. Um, the student details are those one. That's my name, Sekulino Martin. That's my student number, the registration number. Then our group assignments are machine learning techniques for reduces separation. The abstract. This paper introduces deep breath, a deep learning model designed to automatically detect respiratory pathologies in children using lung auscultation recordings. Traditionally, the lung auscultation relies on the physician's stethoscope. That's the instrument they use to listen for abnormal breath sounds. However, this method is subjective to prone to human errors. So deep breath aims to provide an objective and potentially more consistent approach for respiratory disease detection. Um, this is a computational problem. The paper addresses the challenge of classifying lung auscultation recordings into two categories. That's the healthy with the respiratory pathologies, including pneumonia, wheezing disorders, and bronchiolitis. So basically, as I said earlier in the abstract, traditionally the doctors use, or the physicians use the the stethoscope to listen to uh, the lung auscultations in order to classify whether the patient is normal, that's control, whether he or she has pneumonia, wheezing disorders, or other bronchitis. But then this one wasn't consistent because it was depending on the doctor's view, of which the doctor can make a mistake. Maybe the doctor smoked something strong. Therefore, there was need for developing a model which could classify these disorders, which can be more consistent and more accurate, and even more reliable. So the machine learning models, deep breath utilizes deep neural network, which is an architecture that combines both convolutional neural networks and logistic regression. So the convolutional neural network is used to extract features from the raw audio data representing from the lungs, and then the logistic regression model, that's the one which classifies the extracted features into either healthy or pathological categories. So the model operation, first there are basically three. The first is preprocessing, have feature extraction and classification. Now in preprocessing, lung auscultation recordings are preprocessed to remove noise and to standardize it into the required format. The second, that's feature extraction. Now in feature extraction, the CNN, that's the convolutional neural networks, extracts the relevant features from the audio data, capturing patterns indicative of healthy or abnormal breathing sounds. Then classification, finally, the extracted features are fed into the logistic regression layer, which outputs the probability score indicating the likelihood of the recording belonging to either healthy or pathological class. So these are the targets. We have control, pneumonia, wheezing disorders, and bronchiolitis. Now control, that's normal or healthy. Then these ones are the pathological categories, including pneumonia, wheezing disorder, then bronchiolitis. This is a deep breath binary predictions. So basically, as we said earlier, there are four targets. Here they use the deep breath model, which is used here, and they compared it with the baseline model. These were the sensitivity, results, and then the specificity results, then the AUROC, that's the area under the receiver operating characteristic curve. So these are the four binary submodel deep breath and baseline models were evaluated on both internal test folds and external validation data. So the above table is the one for internal test folds, then the last one is for the external validation data. Here this shows the deep breath ROC curve. As we all know, ROC, that's the receiver operating characteristic curve for binary classifier and on external and internal validation data. So each panel shows the ROC curve of one binary classifier. Now in A we have control, in B we have pneumonia, in C we have wheezing disorder, and in D we have the bronchiolitis. So every iteration is nested for every iteration is of a nested CV. CV, it means a cross validation. So every iteration is for a nested cross validation yields for a different model. Model evaluation. Here in model evaluation, the authors evaluated deep breath using several matrices, including area under the receiver operating characteristic curve, that's the AUROC, which measures the model's ability to distinguish between healthy and the pathological class. So the higher the area under the receiver operating characteristic curve indicates better performance. Then the sensitivity and the specificity which we are talking about, this assesses the model's accuracy detecting the true positives, that's the pathological class identifying correctly, and the true negative for the healthy cases identified correctly. So this is a deep breath confusion matrices for multi-class predictions. So a confusion matrix was computed for every CV model. As we said earlier, the CV is a short form for cross-validation model. So the CV model on the corresponding folds. So A, this is the first graph, is for the internal confusion matrix, which was obtained by taking the average of the intermediate confusion matrices. Then B, that's the external confusion. This is the second, the external, for the external confusion matrices, which was aggregated and aggregated patient predictions. This slide is the example attention curve, which returned by the CNN classifier that discriminates the healthy recordings from the pathological ones. The attention curve are overlaid on the recording spectrograms. That blue curve is overlaid on the recording spectrogram, which are given as input in a CNN classifier. So depending on the MAD, the MAD value. So the MAD in full, that's the mean attention difference. So the mean depending on the mean attention difference, either the expression phase, the expression expiration phases are provided as a reference, and then the respiration phases are extracted from the recording annotations. So the recording have the negation, and its attention curve is shown with the inspiration phases. That's in A. Then in B, the recording are on a positive mean attention difference, and its attention curve is shown with the expression expiration curve. So these are the participants and the cohort description. It's just like the database. Remember on the title they talked of the 572 outpatients and 5 countries. So the 5 countries, it included Geneva, that's from Switzerland, the POA, that's the Porto, Algeria, then including Brazil, then we have Dakar, which includes Senegal, and then we have the MAR, that's Marrakesh, including Morocco, then you have the Rabat and the Yaoundé from Cameroon. So after diagonizing them, they found out that in Geneva there are 23 Control, we said control means healthy, then 27 with pneumonia, to 66 with breathing disorder, then 4 with bronchiolitis. And then in POA, that's Porto Algera, they found out 80 with control, which were healthy, then 38 with pneumonia, and so on as shown in the table. So the data set in this paper was partitioned. The data set was partitioned, as you can see. First, we have Geneva and POA. These were used in training, and testing. Then the remaining 4 they used in what? In external validation. So Geneva and Porto Algera were used for training and tuning, and then model selection and testing. Then for external validation, were performed on independently collected recordings from Dhaka, Marrakesh, Rabat, and then the YOA for cross validation. The overview of the depth binary classification model. First, in binary classification architecture, it's trained for each of the 4 diagnostic classes from top to bottom. First, A, you have data collection where they got recordings from 8 points of the lungs, from the anterior and for the posterior. So they got the sound signals. These sound signals in B, they are pre-processed by using a batch filter. In B, we use a batch filter which is applied on the clips before transformation into the log-mail spectrograms. So the log-mail spectrograms are then batch normalized and then augmented. Then the results are then fed into the audio classifier, which produces the probability and the attention values. Then the two are aggregated into a single clipwise output for each site. Then these aggregated and the concatenated are obtained from they are used to obtain a feature vector of size 8, which then are fed into the logistic regression layer. So finally, in E, the patient level classification is performed by thresholding to get the binary output. Let's dive into the strength and weaknesses in the paper. First, the strength, we have the objective. It's objective and automated. So deep breath offers an objective alternative to traditional subjective lung auscultations. Then it has high accuracy. The model demonstrates good performance in distinguishing the healthy from the pathological classes, compared with the traditional setting where the doctors use their stethoscope or that instrument. That's that instrument they use. So there is multi-country validation. So training and they trained and validated on data from various countries and potentially improving the generalizability. Finally, the weaknesses is limited to pediatric population. The model is currently trained on pediatric data and may acquire further development for adults. Pediatric means for only children. So the other weakness, it's a black box in nature. So deep learning model can be complex and difficult to interpret, so limiting the understanding of their decision-making processes. Then it's real-world performance. The paper's evaluation is based on simulated data, and real-world clinical validation is necessary. Finally, they have the critical analysis. Deep breath represents the significant advancement in the field of automated respiratory disease detection. The use of deep learning provides a promising approach in analyzing lung sound and potentially improving the diagnostic accuracy. Thank you very much for listening.